Let's get started on interval estimation, or finding confidence intervals is the way you normally say that. So the next section is a couple of things we will be doing: constructing confidence intervals for mean, proportion, interpreting it, and describing what that means. So first, a little background on what this is. The concept is this. So we say, you can copy that bell curve in a second, but we say that an estimator, like X bar, has a certain chance, to be inside an interval. And we'll talk about the actual language and all that next. Okay, so it's inside this interval. I'm making this just simple right now. We say, so another way of stat language, we are fairly certain. So fairly certain an estimator lies inside. Estimator lies inside. There's always outliers and things like that, but we're saying most of the samples will be inside that interval. And that's the concept of confidence intervals. All right, so so draw the bell curve. I'm basically copying the built-in thing just to make it look nice. These represent the standard deviations, but we don't need those right now. I just wanted to show you the bell curve. So in general, the green area, so this is review and background. So the green area alpha is alpha. So consider that piece that the green area is alpha. So if the entire thing is shaded, then the area of alpha must be what? Underneath the curve for a normal distribution has to be 1. That's the whole concept. So that area has to be 1. The probability of any variable pertaining to that must equal 1, or we say 100%. Okay, so this is review and background. Okay, so now we're going to look at the confidence intervals, because we can never be 100%. All right, so let's take a look at these confidence intervals. So I'm going to copy that again and redraw stuff. So let's duplicate it and copy it down here. All right, so then I'm going to delete some of this. Delete that one. Oh, deleted them all. That's fine. All right, so these tails in here, let's suppose those were green. That's fine. Suppose these tails here are green, like this. Okay, so that side and this side. So that total area of those tails we're going to call alpha, both of them, the sum of those. So the sum of both of those is alpha. So that means, zoom in a little bit, that, so the area alpha is the sum, oops, not sum, the sum of both sides. And we call those tails. All right, so that one and that one. So that means each one has to be alpha over 2. It's alpha over 2. So if that's the case, then what is the middle? What's the middle part? So all of this, oops, didn't mean to do that. Like that. So what is all of this? So if the green is alpha, and all that region has to represent what? Algebraically, you write what? You write, because the whole thing is 1, right? Okay, so the whole entire area under the curve is 1, and we're getting rid of each of these sides, here and here. So that means this area must be 1 minus alpha. So that's 1 minus alpha. So what you get is the total area minus the ends. I just put that in quote, minus the ends of it. Or you're subtracting those pieces off. The middle has to be 1 minus alpha. So that's what we're concerned with. That's what we want to look at. And if this middle part here is 0, and we're doing like a z-score, putting everything at 0, then you go out to, you call this value there z sub alpha over 2, and this one here negative z sub alpha over 2. That's how I indicate it. And so we'll get specific numbers here in a second. All right, so then all right, so that's what the confidence interval is. It's in between those two values, and that's how you create the confidence interval. So we will create confidence intervals. Typically, you have 90% confidence intervals, 95% we have done, basically. We'll look at 98%, 99%, and then you can go higher. But these, the decimals, of course, are 0.9, 0.95, 0.98, 0.99, etc. Okay, so those are the confidence intervals we will create, and these values in between is the confidence interval. So that's what we, oops, we went a little too far, didn't I? So from here to here, that's what we mean by the confidence interval. And so we will say it's 95% likely that the mean, or whatever metric you're looking at, or not metric, but whatever statistic you're looking at, lies in that interval. Okay, so the way you describe that is we say 0.95 is equal to 1 minus alpha. That's the area inside of it. That's the 95% confidence interval. So you look at 1 minus alpha. Or you could say 0.99 is equal to the 1 minus alpha. And that allows us to solve for alpha as well. And percentage-wise, you'd say 95% is equal to 100% times 1 minus alpha. 99% is equal to 100%. That's what you'll see in the book, 1 minus alpha. So coming back to the other, let's see, let's find the z-score for that. So we already looked at what that is. It's got to be the 1.5 0.96. So we'll look this up. For a z-score at 95% confidence. So this is some of the language that we use. 95% confidence interval is between negative 1.96 and 1.96. So when you solve that, so you say 1 minus alpha is equal to 0.95, then you can solve for the sum of those two alphas. So you have, so this is equivalent to if and only if alpha is equal to 1 minus 0.95, which is equal to 0.05. And so when you do alpha over 2, therefore alpha over 2 has to be 0.025. And that's the area of those ends. So if you look at, actually, if I can paste that again, I will. So let's see. Yeah, that worked. Okay. So I can erase that. And this time we're going to erase that. And I'll try to erase that as well. Let's see if I can erase that and that. Okay. So now I can construct this one, do my own thing, of course. So for here, let's see. It's fine. So if you're here, you go up to here, whatever that is, visually, just different curves, whatever. That's your z equal to negative 1.96. This is z equal to 1.96. And so this is your 0.05 over 2, which is 0.025. Same thing here, 0.05 over 2, 0.025. That's your area. And so everything in the middle is 95%. So all of that. So 95% of the data or cases will lie in there. There's your 95%. And you can adjust that. If you want a bigger, more confidence, you go farther out. Narrower, we don't usually go narrower, but you could. You could go, see, sometimes you're only concerned with, 75% of the population. Like that's all you care about. If you can get 75% of something, in most cases, voter concepts, those ideas, that's plenty. So you can go down, but usually for confidence intervals, we stay up there. But again, the research element of it, that's a different class, different methodology in what we're doing. All right, so our goal is to calculate a confidence interval for a point estimator, such as X bar. That's the most typical one we will be concerned about. But you could look at sigma. You could look at or S, the standard deviation. Like what's how confident are we that that's the real standard deviation, that kind of thing. All right, so let's look at just a basic example and how to do that calculation. Okay, so this is still So we're centered at 0. Like we're not getting an estimator yet. We're not deviating. We're just doing z-score stuff. Now we're going to say plus or minus, adding on to the x bar and subtracting from the x bar, and what that looks like. All right, so suppose, let's come down here for this example. All right, I'm going to copy some of this over from my lecture notes. So here they are, which you may or may not have them at this point. Okay, but let's copy that over and write it down. It is best to write these verbatim as we go. All right, suppose we have a sampled population of n equals 100. We calculate x bar and s from that sample. Easy enough. From the sample, all right, we want to know the likelihood mu is close to x bar. That's the idea. To do this, we construct a confidence interval. So that's what they call them. They call them 1 minus alpha confidence intervals. Okay, and this is how you do it. You do your x bar, whatever that mean might be, and then plus or minus the z-score. That'll be 1.96 if it's 95%. It'll be higher if it's like 98, 99%. It'll be lower, smaller number if it's a bigger interval, smaller interval. Times the standard error, okay, or SE. And so those are the square roots and stuff that we just did above. All right. So all right, so a couple different ideas here. If x bar equals mu, the standard error must equal 0. Then there isn't an error. So if you do the calculations and you get 0, then it isn't. But you don't know that. You don't know what mu is. But if it happens to be the actual population, then that's what you would get. Okay, so we are estimating if the sample resembles the actual parameter mu. That's what we want to find. All right, so let's look at an example. So for example, let's look at so consider the actual GPA of, let's just say, Chaffey College students. Chaffey College students versus a sample. And that we have to say for n greater than or equal to 30. Now, just on a side here, what would make the sample biased? For one, if you just sampled, say, math and science majors, that would be a biased sample. If you just sampled, if you just sampled other majors, right, just in particular groups, you want really, in that case, it's difficult to get an unbiased sample because you have to look at all these different groups, right, of what it would be. All right, so now we don't know mu. You do in a college because you have the transcripts, but let's just suppose you don't know that exactly. It'd be difficult to know sigma if you don't know mu. So here's one of the tenets I'm talking about here. So it would be difficult to know the actual standard deviation if we can't find the actual mean. Right? I mean, if we can find the actual mean, then we should be able to find standard deviation. But if you can't find the actual mean, then how do you calculate the standard deviation? So that's where we pretty much always use S. We will use S for calculations. All right, so a couple things. So remember, S, the sample, is always greater than sigma. So the sampler standard deviation is always greater than the actual standard deviation because you're dividing by one less degree of freedom. So when you divide by a smaller number, the number's bigger. Okay, so it's n versus n minus 1. So it's always bigger. Okay, so there is a there is a greater variance. There is a greater variance or larger interval. So it's a larger interval using S. Okay, so think about that. All right, so let's look at how you do this calculation. So a 1 minus alpha times 100% confidence interval for X bar, so it would be the mean GPA, would look like this. You'd say X bar plus or minus Z sub alpha over 2 times S over square root n. And then put that into an interval, and it's the interval X minus Z sub alpha over 2, S over root n, comma, X bar plus Z sub alpha over 2, S over root n. So that was considered the point estimator, but it's really just putting into the interval. So that we really talk about intervals mostly, and we'll do that calculation. So, oops, don't want that. Let's look at another, bring this down to do another visual depiction of this. Let's copy that, bring it down here and paste, and we gotta delete a bunch of stuff, but that's okay. Okay, so let's delete that, all of that, all of that, and that. All I want is the curve, because those are, it's difficult to draw those symmetric, because normal curves are always symmetric. There's no skewness to it yet. So that confidence interval is going to go to here. So this, that's the interval we're looking for. Constructing that, like what are the actual values? All right, so this is your X bar minus Z sub alpha over 2, S over root n, and then to here is X bar plus Z sub alpha over 2, S over root n. I should point out some places they'll use sigma here. In practice, it's really hard to use sigma. Oh, in the middle, so this is your X bar. Well, the middle you can assume is mu or X bar, but we don't know if it's really that. That's what we mean by the confidence interval. So the probability that this value that mu is between these values, this is really the punchline here, the probability that the actual mean is between this value and this value is 1 minus alpha. That's this area. Okay, so this is your 1 minus alpha. So when you do that calculation, that's what we're saying. So you construct it to be whatever percent we're looking for, 95, 99, etc. Okay, let's do this example. I'll pull over the question and we'll write it out. And yes, I know it's just right there. You can like see it and copy it, but let's just copy this over. I think I grabbed some of the work this time. So copy that. So that's the question. Whoa, that was weird. Strange. All right, so it's okay. This will work. All right, so we can start there. That's fine. Suppose that a random sample, oh, that's why I did that. I was zoomed in. Let's do this. I was wondering why that happened. Okay. Suppose that a random sample of size 100, this is a generic question, nothing specific, but you get 100 of anything you want, is selected from a population of sample variance, S squared is 25. The sample mean is calculated, right, to be 35.6. Find a 95% confidence interval. Looks like I messed up the L there. And so you start writing down the information. You're given your sample size, that's your N. You can calculate your standard deviation. Sample standard deviation is 5. And then it said 95%. And then we know for 95%, your z-score is 1.96, which we did that calculation earlier. All right, so let's do the calculation. Let's find out what the actual numbers will be. So I like to do these separately. So let's calculate. Where is it? Oh, they're pretty. This one's pretty straightforward. You can pretty much just write it in. So it's 35.6 plus or minus the 1.96. Right, that's your z-score at 95%, times S is 5 over the square root of 100, which is, of course, 10. Okay, then we can write that into, simplify it, so 35.6 plus or minus 1.96, that's 5/10. Okay, we can do that part on your calculator, 1.96 times 5 divided by 10, or you can move the decimal and multiply by 5, is 35.6 plus or minus 0.98. Okay, then we put that into an interval. This is your confidence interval. This is it. This is the big time right now. You subtract 0.98 and you get 34.62. You add 0.98 and you get 36.58. And I say 6 is 34.62, 36.58. So and then what you say or interpret is we are 95% confident that the true value, so that the true value of mu for the population is somewhere between 34.62 and 36.58. So it gives you basically a range, upper bound, lower bound, and that's your confidence. So be able to construct, do this construction basically of a confidence interval. So try different, you could do this same question and try a 98% or 99%. And we'll do one later for those different cases. Next, we'll do population proportion example. For population proportion, the rationale is really the same, just using those formulas. So a 1 minus alpha times 100% confidence interval for the sample proportion p hat. So it's plus or minus p hat plus or minus the z-score, which will be whichever one we're looking at, right? And then times the square root of p times q over n. And you won't know p or q, so you have to use that for your standard error. And then there's your confidence interval. So we need to know how to construct those confidence intervals for proportion. All right, so we do not know p, so we use p hat or q hat. And always don't forget what q hat is. So q hat is always 1 minus p. It's easy to calculate, and you just put it in there. All right, so let's go ahead and look at this example for rocking the boat. It doesn't really matter what the questions are, but just wanted to show you this one specific from the text. All right, so how likely are they to vote in the next election? Presidential, a random sample of 300 adults was taken. 192 of them said they always vote in the presidential election. Construct a 95. Oh, I did 95% again. Let's do it differently. Let's construct a different percentage. So let's just do 98%. Or I have 99 down later. So let's construct a 99%. Okay, so let's do 99%. Confidence interval for a proportion of adult, etc. Okay, actually, let's just do. We'll stick with the actual question, just because the next video will have different percentages. You can look those up. Usually, those are right in the. There's they tell you what 99, 95. You just look them up, what the z-scores would be. But I'll show you how to calculate it again later. All right, so let's start writing down our information. So you want to write down the data, so what you're looking for. So we need n. So n is given to be 300. You always want to know your sample size in n when you look at statistics. Okay, so p hat will then be what? Well, you did 300 adults. 192 said they would vote. So it's 192 over 300. You divide that on your calculator and you get 0.64. 0.64. Okay, so for 95% confidence, your z-score, alpha over 2, and actually let me write it this time. This is z sub 0.025 is 1.96. So when that changes, you use a different value and you just do the calculation. All right, let's calculate the square root now. So doing this a little separately in pieces. The square root of 0.64 times, and I don't know q, so we'll just do 1 minus 0.64, like that. And then we divide by 300, And then you can write that out in pieces. I think I did a couple steps for you. Square root of 0.64 times, that's 0.36 over 300. So you do that inside part first, and then you hit the root button. And I did another step for you. Like how? Square root of 0.000768, which equals, when you do it square root, 0.0277. Right, so I just did this calculation here. Let's just use orange. Okay. So I just did this. We need that. That's this right here. Now we need to multiply by 1.96, or again, whatever confidence you want. Basically what it's doing is just widening or making smaller the interval. If it's 85%, you can make it smaller. You should be confident that 85% will be in the interval. So 1.96 times that, 0.0277. Did this all on my calculator, 0.0543. So you may want to try it and confirm all that. And then the interval, confidence interval, is your p hat plus or minus that. So it's minus 0.0543 to p hat plus 0.0543. Okay, so we'll do that calculation. So that's 0.64, which we calculated earlier, minus 0.0543 to 0.64 plus 0.0543. Calculate that, and your confidence interval is 0.586 to 0.694. Okay. So we are 95% confident that that's a correct ratio, that 64% of the or what was it? Yeah, 64% of the population will vote. So what was the question? Let's see, what did it say? Okay, so that's the confidence interval. That's A. So A is done. I took off B because it wasn't relevant to what we were doing. Or C, I'm sorry. C. I took off C. B is here. An article in American Demographics reports that percentage of 67% based on interval, okay, would vote. So 67% is in here. So that's 67% is inside that. Would you disagree with their report percentages? Explain. And I would say no, because you are 95% confident that that 64% will vote. That was your sample, but 67 is in that interval as well. So if they said if they said 75%, then you'd say no, that's outside, that's way out here. So 67% is reasonable, and I'd say yes, that makes sense. That I would agree with what they said. It's maybe a little high, but it's still in the reasonable amount, because 95% confident that will be inside that interval. Okay. Next, we'll go on to the two sample means and proportions.